So this title says what we're going to prove. Regular plus second countable is normal. But first we'll prove a consequence of just second countability, the Lindelof property. Okay, so we have seen open covers before, so let U alpha. Okay, so since I started writing it, let's write it this way, not script. So let U alpha in A be an open cover of, let's say X, but I'll make a blanket assumption X is a second countable. Topological space. I won't assume regular here because the first result doesn't need it. So let U alpha be an open cover of X, then U alpha has a finite subcover. Okay. Well, so first of all, note that we have a countable basis. So let Vn, n in n, why not index it by natural numbers, be a countable basis. Now any open set is a union of basic open set. So countable basis for X. Okay. Then each U alpha is the union of basic open sets. So each U alpha can be written, no need to write it in minimal form, we are only after countable ones. So it's the union of the set of all union of all Vn such that Vn is contained in U alpha. So if I look at the basic open sets that are contained in U alpha, the union will give U alpha itself. So V sub n, this is V sub n is contained in U alpha. So U alpha is the union of these sets inside it. So that's nice. Hence, X is the union of U alpha, because alpha is an open cover. And hence it's also the union of Vn such that there exists alpha such that so Vn is contained in U alpha. So it's the union of these basic open sets which are contained in some U alpha. Okay, these are only countably many, which is countable. So this is countable. Well, that's not yet given a subcover of alpha. Okay, so let's call this set. So now, so hence, okay, so now I have to give these things names. So let's give some ad hoc names. Let's just identify those n. So let some Bu, B of U, be the set of all n in n such that Vn is contained in U alpha for some alpha, and for each alpha, for each n in B of U, choose alpha n such that, so I could have written alpha n for some alpha n, so such that Vn is contained in U alpha n. So now therefore X is going to be union alpha in A of U alpha, which we already observed is union of n in B of U. So script U is this whole collection. Script U is this whole open cover, so it's a function of U of Vn. But you see, Vn is contained in alpha n. So this is union n in B of U. Okay, so this B of U is a subset of natural numbers of U alpha n. And this is countable. So U alpha n form a countable subcover. So in case the idea got lost in the details a little bit, let me quickly go over the idea. The idea is you have perhaps a huge cover which has lots and lots of sets. Now each of these sets is a union of basic sets. But there are only countably many basic sets, and we don't have to take a set twice because it comes in more than one U alpha. So we just look at what basic sets to include and what to exclude. We simply include only those that are contained in one of the original cover. When these are included, what you end up with is a cover of the given space. And when you have this cover of the given space, so this is fine, but this is a countable cover by the basic open sets. But the thing is, each one of them is contained in some U alpha n. So I only take those U alpha n which have this role of enclosing one of the basic sets we needed. And hence, we have got a countable subcover. And now with the Lindelof property, we can prove the following theorem. If X is regular, then X is normal. You may wonder what's the big gain in having a countable cover. Lots of things are countable. The thing is, very often we are taking covers with one point for every point in a set. I mean, with one open set for every point in a set, as we will do just now. Okay, and then that's a lot bigger than a countable cover, and we want to cut it down. And as I said, we have to, regular does not imply normal. We'll eventually see counterexamples. So here X, which remember is second countable here. Okay, so let A, B and B be disjoint closed sets. We want to separate them. Okay, so here is A and here is B. Now using regularity, we have covers. Let me just directly say, and Lindelof will let us cut the size. We have covers, they'll become countable because of Lindelof, but we have covers un of A and V, let's say M of B, so both indexed by natural numbers. The shortening comes by Lindelof, but the main covers comes by regularity, such that un bar intersection A is empty for all n, and un bar intersection B is now empty, and Vm bar intersection A is empty for all m. So because we have regularity, so if I have, for example, un bar, I'm using the fact that B is closed, and for each point little a in A, I can find an open set that contains it and an open set that contains B, so that these two are disjoint. So the complement of this open set containing B is closed. So this open set is contained in a closed set which is disjoint from B. So in fact, the closure of this open set is disjoint from B. So we are using the regularity in a strong way. It's not just this open set is disjoint from B, which would come from the fact that B is closed actually. We're using the separability. And reversing the roles, we get these sets. So now we have a sequence. Now what we'll do is we'll make them disjoint. Okay, so what we'll do is, given this set, well, these sets might overlap. I may have a set here and a set here. But from each of these sets, I will get rid of the intersection. Well, that could be a problem because we have to get rid of too many intersections, but we'll get rid of the previous set's intersections. So let me be precise here. Let un prime is un minus union I equals 1 to n of Vn closure, Vi closure. So from nth term, we get rid of the closure of all the previous sets, and similarly Vn prime is Vn minus union I equals 1 to n of Ui bar. Key point, then un prime and Vn prime cover A and B. Okay, so if U is the union of Un prime, n is 1 to infinity, and V is the union n equals 1 to infinity of Vn prime, then they are what you would want with normal sets. A is contained in U and B is contained in V, and U intersection V is empty. Okay, so first let's see, why do they cover? We have cut out some pieces. Well, UN's cover, that is by construction. So V's cover. We have cut out some pieces, but we know the closure of this is also disjoint from A. So we have not cut out anything in A. So, and we have cut out only finitely many, so it remains open. So these are open covers, so their unions are open sets containing these. And now if I have a point in both of them, well, it has to be in some Uj and Vk, with the unions, because they are contained here. And let's say j is greater than or equal to k, then we have deleted Vk bar even from, we have certainly deleted Vk in getting Un prime. So it's not going to be in Uj prime. So if it is in some Un prime, it is also in the Uj prime as well as Vk prime. It has to be in the corresponding Uk and Vj. But then we see that we have removed everything from the previous sets. So the trick is that because we don't have to remove everything from one, if we are looking at a pair, either the first one comes before either if we are looking at an intersection of a pair here, either this guy comes first or this guy comes first. Okay, so essentially we are looking at intersection and distributing it and looking at it as a union of intersection of pairs. Okay, so formally, so U intersection V is formally the union of the intersections over Jk of Uj prime intersection Vk prime. And what we claim is that if j is less than or equal to k, then this is empty, and same if j is greater than or equal to k, for different reasons, because we have deleted the set overlaps of all the previous sets. So with finitely many deletions, which leaves it open, we still have the intersection being empty, and hence we get this is exactly the claim of normality.